Hello, my name is Rhodes Foster, and this is my Physics 2211 Lab 3. Looking at some of the content that I'm getting into today, we have an introduction, models, data, and observations, we have some code, and a discussion at the end. The purpose of the lab is to calculate the mass of a black hole and the initial velocity of a spaceship required to orbit the moon and planet. Some of the fundamental principles at play here are Newton's second law and the law of universal gravitation. For a little preview of results, the black hole's mass and spaceship's initial velocity can be found using some unique GlowScript code. Getting into some of the laws at play here, Newton's second law, known as the momentum principle, states that a force is equal to the change in momentum over the change in time. It's going to indicate changes of movement within the system and its surroundings. This principle is going to be in use when trying to calculate the forces on a star and how this influences the initial velocity of the spaceship. Another force at play here is Newton's universal law of gravitation, stating that every object with mass attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. It's going to describe how gravity acts between objects in space and Earth. This principle will be in use when determining the gravitational pull between planets or calculating how gravity is going to affect the motion of our spaceship. So for part one of this experiment, we're going to analyze the motion of the unique star through GlowScript code to find net force and really calculate the mass of the black hole. For part two of this experiment, we're going to use the mass of the planet, spaceship, and moon to calculate all the forces on the moon and all the forces on the spaceship. We're going to play around with GlowScript a little bit to find the initial velocity that's necessary for the spaceship to avoid hitting the moon or planet as it orbits them. Still looking at parts 1 and 2, the system for part 1 is the star, and the surrounding for part 1 is the black hole, while for part 2, the system is the spaceship, and the surroundings are the moon and planet. Focusing on part 1 here, we made the position of the black hole 0, 0, 0. We edited the mass of the star to be 2 times 10 to the 30 kilograms. Again, we don't know what the actual mass of the black hole is. And then our GT email is initially added as the seed of the code so we can randomize the experiment. It can be assumed that there are no external forces acting on the system. Now we're going to focus on part 1, and I'm going to demonstrate my code. On the left here, you'll see my edited code. And essentially what I did was I inputted a few equations that I'll talk about here that were needed to actually calculate the mass of the black hole. We have the mass of the star, we had the initial and final momentum equations, change in velocity momentum equations, change momentum, FNet parallel and perpendicular equations, and again, we're all going to use this to calculate the mass of the black hole, and obviously I inputted my email for the seed for part 1 of this experiment. Getting to the results from part 1, the mass of the black hole was found by using the normal gravitational force equation and isolating the black hole mass. For each data point in the star's trajectory, the net force was calculated from the change in momentum, then used to back calculate the black hole mass using F equals GMM over R squared. We averaged this across all the data points, and we found the black hole mass to be 1.00329 times 10 to the 34. Now we will get into the second part of this experiment. So here we altered the starter code, we changed the moon speed, the ship speed, the net force on the moon, the net force on the ship, and the movement of spaceship and the moon. So obviously I had to play around with ship speed here to get that shape that we will be looking at in the upcoming slides. So yeah, here's the shape that we yielded. So using the new code, this model was produced showing the ship, which is the pink line, moving right around the planet, which is the blue dot, without hitting the moon, which is the cyan line. The initial velocity of the spaceship was negative 400 meters per second in the x and negative 400 meters per second in the y.
Since there is no tangible experiment, there's little room for error. However, it's possible that a value is incorrectly calculated due to a mistyped formula. Also, there might be variation among different students.
Let's talk about what this might mean. So, net force parallel and perpendicular in this case is numerically the same as the change in momentum parallel and perpendicular. The difference here is that net force is the sum of all the forces acting on the object, while change in momentum comes down to change in the motion of the object. So what if? What if we are predicting the motion of the entire system, including the planet, moon, and ship by each other, and the black hole? We would need to find the net force by each of these individual forces. We would need to apply Newton's second law to determine velocities and positions. The ship would need to have enough velocity to maintain orbit around the black hole, planet, and moon without crashing, and the gravitational force of the black hole
on the other masses is going to be the dominant interaction.